Hi, welcome to lecture 23. We're going to be covering section 4.4 in the Jayam book today. That is concerned with Venn diagrams, but we're going to first revisit a little something from 4.3. Uh, Here's the layout for today. I'll do just a quick little thing on some additional stuff that you should be aware of from 4.3. This is actually covered sort of in the exercises strictly, so it's not in the text of the chapter, or section, but it is covered in the exercises, and I think it's worth spending a little time on to get straight. Then we're going to look at a topic called Jordan curves, and those are an essential ingredient into making Venn diagrams, which I believe most people have played with before, but we'll see some, we'll have some additional fun with them. All right, so let's roll. The new stuff or the additional stuff that I want to highlight from 4.3 is a different way to show the two sets are equal. And it's essentially, well, they call them double inclusion proofs, so that probably tells you what it means. They're proofs where you show that both inclusions are true. A is a subset or equal to B, and B is a subset or equal to A, and that means they have to actually be equal to each other. Rather, like if you think about that with numbers, if A was less than or equal to B and B was less than or equal to A, that doesn't leave a lot of room, does it? They have to actually be equal to each other. So it works the same with sets. Um, a good way to do what I just described, this double inclusion thing, is known as element chasing. So we chase the elements around to figure out where they live, where they are. So all of that essentially means we go from making statements about sets to making statements that literally are statements that are logical statements of the form X is an element of something. Because X is an element of something is a logical open sentence. So it's the sort of thing we dealt with back in chapter 2, logical statement. So yeah, here's the way an element chasing argument would work. You'd first suppose X was in A, and then blah, blah, blah. You'd argue away until you finally conclude that X is in B. And then you'd say, well, now let me suppose X is in B, blah, 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 some different steps possibly, and then get that X is in A. Once you've done both of those, it's well understood that you've showed both directions of inclusion, so the two sets are equal. So I'm going to do an illustration of that approach by proving one of the DeMorgan's laws in this style. The form of this is rather like the ones we did do last time, but it's just that we split it up into showing one direction, then showing the other of these inclusions. All right, so here's the DeMorgan law. The theorem at the top of the slide here is the theorem the version of DeMorgan's law I'm after. So this is what I would call the union version. You're taking the complement of a union, and it becomes the intersection of two complements. So how's the proof run? This is a fairly good way to lay it out, I think. You tell people what you're doing. So first we will show that the complement of the union is contained in the intersection of the complements. Towards that end, suppose X is an element of the complement of the union. All right. So then it goes into a two-column format, which is, this is an appropriate format to drop into since we're in a relatively simplistic setting. So we'll say the given statement is that X is in this complement of A union B. What does that mean? Well, it means it's the logical negation of X being in A union B. So we've just basically applied the definition of the complement. Inside the parentheses here, now I'm going to pull apart the union. If X is in the union of two sets, well, that means it's in one or it's in the other. So if you did one of the exercises in the last section's activity, it was to do the following. When you see an or an and, look on either side of it and make sure that that's a logic thing, not a set. And when you see a union or an intersection, look on either side of that and make sure that's a set and not a logic thing. Okay, so I'm just mentioning that because it's a good thing to check kind of as you're going along. I've got an or here. This had better be a logical open sentence next to it. X is in A is a logical open sentence, and so is X is in B, so that we're golden. All right, so then what actually makes this argument work is that we already know DeMorgan's law applies in logic. So this is the disjunctive form of DeMorgan's law. I'm negating a disjunction. So I get the negation of two things with a conjunction in between them. Right? Okay, where we go from there? Well, those are the negations of two things that look like X being in a set. So that's the very definition of X being in the complement of that set. All right, and then we have X is in the complement of A and X is in the complement of B. Well, that's an and between two membership conditions. So we get the intersection of those, but those things were complemented. So it's the intersection of A's complement and B's complement. Well, that was half the argument because these arrows here are going one direction. I didn't do if and only ifs. In fact, I believe this thing could have been done in an if and only if way. A lot of times I've found that I start out going the double inclusion route, and then I realize, gee, all these implications are actually biconditionals. Well, that's what happens. You write a draft, you realize, well, there's a cleaner way to do this, and then you rewrite it in that cleaner way. I just also noticed there's sort of an extraneous pair of parentheses here at the end. I didn't need those parentheses. And in fact, I didn't need the parentheses around the things above it either. Those logical sentences. The only way this and could make sense is if it was applied to the entire logical statements on either side of it. So the parens are not needed. I think this parenthesis sort of is needed. Not, well, at least visually it's needed, but maybe not necessarily with. I'm not going to worry about too much because a few extra parentheses aren't going to hurt anybody and maybe it helps the readability. Okay, so we still need to finish the other direction here. And you'll see that this is actually the same statements as were on the last slide, but in the reverse order. So in fact, this is a reversible argument. The thing could all be done with biconditionals there. So nevertheless, let's read through it. Next, we'll show that the intersection of these two complements is contained in the complement of the union. So to do that, we're going to start with thinking about an element that's in the left-hand set, the intersection of the two complements, and then jump into the two-column mode. X is in this intersection of the complements is given. What do we do next? Turn to a set intersection thing into a conjunction of the membership conditions. That's what we did. So that's really just what the definition of intersection means. Oh, I was redundant there. That is the definition of intersection. Now, the definition of complement is that you really are, it's the negation of the membership condition for the uncomplemented set. So X being in A's complement is the negation of X being in A. That's the definition of complement. We're actually applying that twice because we're also going from X being in the complement of B to the negation of X is in B. I should point out that writing something like, negation of X in A is fine, but it's also the same thing, if you want to be a little more brief, to write X is not in A. It's the same thing. It just doesn't quite look like we're doing the DeMorgan's law thing from logic if I write it this way. So I'm writing it this way just to make it very clear that the tool we're using along the way is one that we're actually allowed to use, the DeMorgan's law. And here it comes, right? This is the negation of a statement ANDed with the negation of another statement. By DeMorgan's law, that's the same thing as an OR of those two things with a not on the outside. So that's the disjunctive version of DeMorgan's law. Finally, working inside the parentheses, again, I've just noticed I have an extraneous set of parens in there. We didn't need those. But anyway, inside the parentheses, the OR of these two membership conditions, X is in A ORed with X is in B, that means X is in the union. That's the definition of the union. And then finally, taking into account that not that's out front, you get that X is in the complement of that union we just discovered. So definition of complement is the uh, justification for that step. Sometimes, I don't know how I feel about this one. I sometimes like to put in a final sentence that says something along the lines of, thus we've shown that this thing is contained in that, and that thing is contained in this, therefore the two sets are equal. Right? Just wrapping it up. But I don't know. On this one, I feel like it was clear. We said that up front. That was what we're doing. So by the time we come to this end of this second direction of proving the inclusion, I expect the reader to understand that we're finished. So QED, QED right there at the bottom. All right. So that's the end of the little bit I wanted to finish with, from 4.3. So let's get started on talking about Venn diagrams. The first thing with Venn diagrams is to talk about Jordan curves. Camille Jordan was a very famous French mathematician. I think there's quite a few things in math that actually carry his name still. Like there's a Jordan normal form in linear algebra. Um, but I believe in sort of more elementary math, the idea of a Jordan curve is the thing that carries his name that has the most, it's the most well known. So, but Jordan did a lot of things in his life. This is probably not one of the things that he would have been terribly impressed with, but maybe I'm not sure about that. Anyway, it's not a huge deal. It turns out to be it's extremely difficult to prove the Jordan curve theorem, but um, but it's really easy to understand it. So we're going to just go settle with understanding this one. We'll take the idea of a curve in the plane is just a mapping from a given interval into the plane. So I'm using the interval 0, 1, which is fine. A lot of people might prefer to use 0 to 2 pi. That would give you an idea that there's sort of an angular parameterization of the curve. But 0, 1 is fine. Whatever the endpoints are, though, you say the curve is closed if you've got that the left endpoint's value, the point that that 0 gets sent to is the same thing as the point that 1 gets sent to. The left side and the right side are equal. That's what it means to be closed. So, for instance, if I draw the number 8, that's closed because I almost didn't close it, did I? So I should make it really get closed up there. Where I started and where I ended are the same point. That's not a Jordan curve, but that's okay. Simple means that I don't do this. I don't do this spot where I run into the curve. I let the curve run into itself. So that doesn't mean this curve is particularly simple in the traditional use of that word. So I could have a curve that does all kinds of nonsense like that, and that's simple. It just, as long as it doesn't hit itself anywhere except where it began and end, it's simple. That's what simple means. So let's say that in a formal way. This is a nice sentence here. For all A, B, and R, if A and B, well, I'm taking A smaller than B, but really, I mostly just want that they're not equal to each other. So if they're between 0 and 1 and they're not equal to each other, then f of A is not going to be equal to f of B. They won't represent the same point in the plane. Okay, so there's one other issue that's a little hard for me to describe to you at this stage in your career. You've talked about continuity of functions. This is a little bit of a hard function to think about, though, because it's going from one-dimensional space, the interval from 0 to 1, to two-dimensional space, the plane, right? So what continuity means for a function is more or less what continuity means for an injection into the plane like this. The best way, I think, though, to deal with this is to say, hold off. You're going to learn what general continuity means in later courses like analysis and topology. And for the moment, just take this intuitive approach. If you can draw the curve without having to pick up your pencil, that's continuous. So both of the things I did up there are continuous. But if I had to do, I've gotten trapped, come back to here, that would be a jump. The thing where I left the page, came over, and went back to the page, That's a discontinuity. So we can't allow those, or we don't want to allow those. If I wanted to have this weird spiral, I would have to arrange to back all the way out again and then come to there. Can't just jump there. I have to make some continuous path that gets me there. So no lifting your pencil. So examples. Well, I guess I sort of already did examples as we went, didn't I? These are all examples of closed curves. This one's not simple. Here, let's do one that's not closed. That's not simple and not closed. Here's one that is simple but not closed. Right? You can is that all the combinations there are? Either end where I began or not, and I either intersect myself somewhere along the route or not. And I think we've covered all those bases. Okay, so here's the Jordan curve theorem. Essentially, it just says if you have a Jordan curve, if you have a simple, closed, continuous injection of an interval into the plane, it'll divide the plane into two regions. Surprisingly hard to prove, but I'll mention you can also do this on a sphere. There's no reason you couldn't draw on something round. You can imagine drawing on the surface of the Earth or a globe or something. But in that case, Jordan curves, the two regions become a little bit tougher to distinguish. Let me just point out an obvious example of this. Think about how the equator is a simple closed curve on the surface of the Earth. It would have to be a pretty big pencil to draw it, but still. It divides the Earth into the northern and southern hemispheres, right? The two hemispheres, and you know which way is up is really just a convention. You know how when on maps they normally seem to show the northern hemisphere as the top and the southern hemisphere as the bottom, but you know if the people who first started making maps had come from the southern hemisphere, they would probably have drawn them the other way around with themselves on top. I've seen maps that are oriented that way too. So that's an arbitrary choice. It's really hard to tell the northern and southern hemispheres apart. I mean, not specifically in the Earth. I can tell, you know, one's got Argentina and the other doesn't. But really, it's two bowls, right? It's two hemispherical things that club together at the equator. So from a mathy perspective, they're very hard to distinguish. I don't mean geography. I mean just as two parts of a sphere. Okay, so a little break for humor. There's a kind of a shaggy dog story about three professionals that are asked to join a little contest. All right, they're supposed to use a certain amount of fence material and enclose the maximum possible area. And so it's an engineer, a physicist, and a mathematician. And the engineer solves this problem by taking the material and very carefully laying it out into a square. He measures it, figures out what 1/4 of the material is, and builds a square of that size. And that's pretty smart because, you know, amongst all rectangles, the square has the most area relative to its perimeter. And then the physicist sees this and he laughs a little bit because I know how to beat this guy. And he takes the same amount of fencing and he puts it in the form of a perfect circle. I hope that looks like it's the same amount. It's supposed to be the same. The perimeter of this and the perimeter of that are the same. So you probably know that, yeah, if you have the same perimeter, a circle rather, is the thing that has the most area amongst all things that have that perimeter. So the engineer realizes he's been beat. And while these guys are working, the mathematician has made this sort of crappy looking small fenced area and he's standing right in the middle of it. And they're like, dude, you're trapped. And, you know, and he's like, no, I'm on the outside. You see why that's funny? He's on the outside. That beats, if he's on the outside, these guys were all over here and they were thinking this was the region. But he's declared himself to be on the outside, so the whole rest of the globe is the region that he's enclosed. Okay, it was a little bit funny, right? Anyway, yeah. If you're talking about the sphere, both regions that you might create will be bounded. So in a sense, they're hard to tell apart. The extreme is when it's the two hemispheres. But if you're working in the plane, one region is finite in area and the other is infinite. One's bounded and one is unbounded. So we typically call the outer one the unbounded region. You have actually encountered that terminology, I bet, when you took calculus. There's a thing that's done over and over again, and they forget to mention that nobody understands the terminology, so it usually confuses people. But they talk about finding the area bounded by two curves. And this is what they mean. The two curves, like if you have, here, let me try a quick sketch. Y equals x cubed like that, and y equals x squared like that. There's a bunch of regions that are around those two things, but there's this little crescent that is in between them and is a bounded region. These other regions are infinite. So when they tell you find the area bounded between x cubed and x squared, they mean that, and you're supposed to just understand that. I think most people look up a similar example in the book and they go, okay, I see what they're doing. The terminology just slides over your head, but now you know. Bounded means it's bounded. All right. Um, here's an example of some thinking about Jordan curve stuff that is really cute. This comes from a math competition that's held up here in New England at the annual meetings of the Math Association of America. Well, the local group, the northeastern section of the MAA. They have this competition for undergrads. So it's usually teams of 3 people from dozens of different schools work on, I think it's like 10 or 12 problems. And you only have like 2 hours, so most people don't finish them all. And it's good fun, though. There's a lot of good problems. And I actually got to work on this competition for a period of time. And one of my colleagues who was working on it came up with this problem in order to honor the memory of Martin Gardner. I forget why 2010 was important. It might have been the anniversary of his death. So, but in any case, let's read the problem. There's a point labeled A, and it's inside a simple closed curve. It didn't bother to use the Jordan curve terminology there, but a simple closed curve that's partially hidden under a piece of paper that has a rectangular hole in it. I'm going to show you the diagram in a second. Is it possible to say whether the point labeled B is also inside the curve? If so, which is it, inside or outside? Now, this guy, Martin Gardner, was famous as a popularizer of mathematics, and he wasn't a mathematician himself. He was a journalist. He wrote for Scientific American and many other magazines and newspapers. But he knew quite a lot of math, and he had a joyous approach to sort of the fun little nuggets you could find in math. And this one is very much up his alley. It involves the Jordan curve theorem. So there's the setup. You've got this piece of paper with a hole in it through which you can see the points A and B and a portion of the curve. There's even portions of the curve that are sticking out on the outside of the sheet of paper. But you don't know what the details of the curve that are hidden are. So is it possible to tell whether point A and point B are both inside or both? I think A was inside, so whether B is inside or outside. Is it possible to tell? Well, I won't hold you in suspense here. What you can do is realize that since it's a Jordan curve, every time you cross the boundary of it, you switch from whether you were in the inside to the outside, or vice versa. So moving from A towards B, I might go down to here, cross the boundary. Now I say A was inside, so now I'm outside. Then I move along to here and cross the boundary. Now I'm the same as A, I'm on the inside, and then I get down here, I'm on the outside, and that's where B is. So I can tell you B is on the outside. It's about the parity of how many times you cross the boundary as you head from A to B. Here's a revealing the secret, right? Showing you the rest of the curve. But it really doesn't matter. You can see from this that, excuse me, B is indeed on the outside. You could also sort of travel from A's position around the curve, and here we are right across from B, and you can see that it's on the opposite side of the wall from us. But the direct thing is to go, yeah, B's got a way out, whereas A doesn't. A is trapped inside this curve if it doesn't jump the walls. Well, that's just a fun example. Anyway, let's get on to talking about Venn diagrams. So what is a Venn diagram? It's just a collection of Jordan curves. So there's generally going to be many of them, although at first we'll start with just one or two. But you're going to have n Jordan curves, and if you do, they will divide the plane into 2 to the n regions. If they don't divide the plane into 2 to the n regions, you don't really have a Venn diagram. Or to be more accurate, you don't have a Venn diagram in what's known as general position. So we're really interested in the general position Venn diagrams where all the possible intersections of the sets involved are displayed for us. So here's the n equals 2 version. I think people have seen this a million times, haven't we? It always looks like the way they show somebody looking through binoculars in a movie. They usually do that, where they kind of make that shape around the whatever the person is supposed to be looking at to indicate the view through binoculars. If you're actually using binoculars, it doesn't really so much look like that. But anyway, there's 3 regions that are pretty obvious to us. There's the part that's in A, the part that's both in A and B, and the part that's in B alone. People tend to forget that there's a 4th region, and that's the part that's outside of both sets. So notice a couple of things too. The union, excuse me, it's not the union. The universe is this entire rectangle. So even our universal set is kind of drawn on the Venn diagram. Oh, I said that in part of the notes for the slides. So the universal set is this big rectangle. All the elements of our sets, of our universe, are inside of the big rectangle, and some of them will be inside the loop for B, and some of them will be inside the loop for A. You don't have to think that every point in the plane is in one of those sets, though. I always like to imagine there's actually like farm animals wandering around in between these things, and some of them have hopped the fences and they're on the outside where the universe that's not in A and B, or A or B, is, but some of them might be trapped here between both fences. Others could be in here. I like to call the thing in the middle, the intersection of both of them, the football, when I'm teaching this to people, and the other things are bitten cookies. See how they look like a cookie with a bite out of them? Those are the set difference pictures. The set with elements of the other set removed from it. That's the relative difference of sets. Anyway, let's go through a few notes about that. I already told you this. There's 2 to the second power because there are 2 Jordan curves, and that gives you 4 regions, and those correspond to the intersection of the sets. A intersected with the complement of B. That's one of the cookies, the bitten cookies. A's complement intersected with B. That's one of the other bitten cookies, and the outside. That's the other piece of this, the part that's neither in A nor in B. These intersections we're seeing here are related to the disjunctive normal form we saw in chapter 2. Remember how that was the or of a whole bunch of ands? Well, these intersections are the ands. So the little sets intersected with the other set with either a complement or not, those are designed to show you all the possible sort of simple regions that you could create in the Venn diagram. Okay, there's not a Michigan effect. What do I mean by that? I do not want to use curves in Venn diagrams. I'll do one last use of this sheet of paper. Here's a thing that I've already started, so this is good. How about if I had 2 of these sort of kidney-shaped things? Would that be valid? Well, then, if this one was A and this one was B, this would be their intersection, and so would this. I can't write small enough to fit it in there, but there's 2 regions that represent the same intersection, or rather, the intersection is pulled apart into 2 pieces. That's what I mean by the Michigan effect. I think most people know Michigan has the bottom part that looks like a catcher's mitt, and then the upper peninsula, and they're only connected by a bridge, not by any land. So I thought I'd take a little break to show you some fun stuff on Google Earth. Where am I looking right now? I think this is somewhere in Denmark. Oh yeah. So we don't want to go there. Let me point out a couple of fun places. Not Point Roberts just yet. Let's look at Kaliningrad. The Kaliningrad Oblast in Soviet, sorry, I was about to say the Soviet Union that doesn't exist anymore. That's a part of the Russian Federation. It is a port, well, it's actually a city that's some ways away from the port, but the port opens up on a nice body of water out here called the Baltic Sea. This is a part of the world near Poland. Poland's down here. The Baltic countries, as they're known, Estonia, Latvia, and Lithuania. But this little chunk right here belongs to Russia, which is over here. So Russia also has the Michigan effect. It's got two chunks. Um, the Russians exerted a fair amount of influence to make sure they got to keep Kaliningrad when the Soviet Union broke up, because it's a port that doesn't freeze in the winter. That is, you can always navigate out of here and get out from the Baltic into the North Sea and out into the rest of the oceans of the world. Russia is a little bit short on ports that don't freeze over and require icebreakers to get you in and out of. So they really wanted to keep Kaliningrad Oblast. Another place that's fun to look at is, I wish it still appeared on my recent searches. There it is, Point Roberts, Washington State. Let's get over here you see we're at whoa, it's weird to zoom like that, sorry. Let's back out a little way so we can see it from a better perspective. This is the northwest corner of the continental United States. Most of the boundary of the continental United States is this 49th parallel, the line 39th or 49th. Well, anyway, that's the boundary. It's the Canada to the north and U.S. to the south. There's this island right here. It's called Vancouver Island, and probably people have heard of Vancouver. It's a pretty cool city. It's not on Vancouver Island, oddly, but in any case, I guess the Canadians didn't want to give up Vancouver, so they had this parallel, this line of latitude, break off before it hits Vancouver Island, and then we sort of work our way through a strait and come. That's the boundary of the U.S. It's got this funny little kink in it right there at the end. But it also has another funny feature on it. The boundary of the United States has this little piece right here, Point Roberts, that's U.S. territory, and it is really connected to Canada. I mean, we actually have plenty of territory that's connected only to Canada, not to the rest of the United States. Alaska is a better example of this, but I figure everybody knows about it. Alaska. Who knew about Point Roberts before? There's like 300 U.S. citizens that live here, and their only way to visit their fellow countrymen is to get in a boat or have a passport, I guess, so they can get around through Canada. All right, so I called it the Michigan effect. I guess we should actually also look at Michigan while we're playing this game. I really enjoy these flyouts they do on Google Earth, where you run away and then. So this is what I was talking about, Michigan. This bottom piece here, where the red tag is, it's actually labeled Michigan. That's the thing that, to my eye, looks like a catcher's mitt. And then this other piece right up here, which is largely the land that separates Lake Superior from the rest of the Great Lakes. But there is actually a river that runs through this little piece right here. Anyway, that's why that boundary looks kind of crooked. But the Upper Peninsula and Michigan proper are separated. There's no land route without going into other states between them. There is a bridge, Mackinac Bridge. Actually, I guess we can see it. Funness to go. Yeah, Mackinac City. That's got to be the Mackinac Bridge. Okay. That was sort of silly, but I did want you to get the idea that we want to have each primitive region that corresponds to the intersection of either sets or their complements have, a contiguous thing, not break up into little subpieces. And I hope that by messing around like that, I made the point to you. So in general, if we're in general position, we will have every possible combination of sets that are complemented or the opposite, not complemented. And that's why, because there's two choices for each of these Jordan curves, which correspond to sets, that's why 2 to the n regions. Good point. you got to remember that the outside is one of those regions. So if you're counting things up and you end up one short, it's likely that you just forgot the outside. Okay, so using a Venn diagram, let me illustrate this with the let me illustrate this with the two set Venn diagram thing. So suppose I wanted to do what it says there to show you what it looks like if A and B are disjoint. If A and B are literally disjoint, I might like to draw the Venn diagram something like this. Here's A and here's B, two separate sets. They lay inside some universe. So we have a Venn diagram that looked like so. But the idea of sort of putting in the empty set symbol to indicate that you've got a forbidden region lets you just use the standard view through the binoculars kind of diagram and still get this point across that A and B have nothing in common. So let's try to replicate the ordinary diagram again. Here's B, here's A. What region is empty if you want to say that A and B are disjoint from one another, that they have no elements in common? I think that's pretty obvious, isn't it? The part that's the intersection of the two of them would need to be empty. So saying this and saying this, they're pretty much the same idea. In fact, they're identically the same idea. And it's kind of nice to be able to just work with one standard diagram and modify it just a little bit to get various results. There's another one on this slide. Yeah, what about if A is contained in B? Let's do that one by quickly writing up a Venn diagram. There's our universe. I try to leave a little break in the boundary of the Venn diagrams to put the letters in. I think that looks nicer. Okay, so if I wanted A to be inside of B, what that means is all the animals that are in here outside of B have to jump the fence and end up in here. So I want this part to be empty. That's the forbidden area. If that region is empty, then we've really said that A is inside of B. All right, 3 sets. Oh, wow, I should have scaled this down so it fits on the slide, but you can probably guess that the third set is labeled C. That's what a 3-set Venn diagram looks like. Now, I forgot to put the things that let us display this a little bit at a time in here, so I've given it away, but that's okay. We've got we're pretty much done. This is the last slide in the deck. So 3 sets. Why did I write 3 sets? I was supposed to say something about it. 3 sets is the last chance you have to use circles as the boundaries of your sets. If you want to do the thing where you make general position happen and you get all the different regions that are possible, all 2 to the n, well, 2 to the 3, 8 regions. Ooh, wait a minute. That's something we should have checked. Excuse me, I should have back up to this. Are there really 8 regions on this picture? There's one. I can't point with my pen at the screen and have you see it. There's one where A is. This region is a cookie with 2 bites out of it, if you sort of see the idea. There's one for B and there's one for C. There's one way down in the middle, and then there's these 3 other ones that look like footballs with a bite taken out of them. How many did I just get? 1, 2, 3, 4, 5, 6, 7. I'm 1 short, right? Because the outside 2, 8. So we do have 8 regions in that 3-set Venn diagram. The point, though, I think I'm looking at an antique version of the slide deck because I remember typing in that it's on GIAM page 190, the 4 sets with ellipses, but it's not appearing right now. That's okay, since we're almost done, I'll show it to you. This is a diagram out of the GIAM book showing a universal set and 4 sets. And it's a little bit of a challenge, but you should try it, count through them, and recognize that all 16 possible expressions that are intersections of A, B, C, and D, and or their complements, appear. So there's 16 regions here. You can't make this happen with circles, but you can if you're willing to relax the rules and do it with ellipses. There's a Google search that I want to run. I think I did it already. No, I didn't. So let's just get a fresh one here, and we'll search for Venn diagrams. Venn diagram for 5 sets. I think that's what I searched for last time. And this, I think, is kind of amusing. If you check out the very first one that comes up, am I allowed to make this look big? Can I maybe open it in a open image in new tab? There it is, good full size. This is showing you 5 sets done with circles, and I just said that's impossible. So here's a challenge. Do we really have all the regions that 5 sets should create? 2 to the 5th is 32. You think you see 32 regions here? I guarantee you don't, because you can't make this happen with circles. The way they're labeling things is kind of clever. Like here's A, just A itself. This is the intersection of A and E, and it's basically not saying the things that it's the intersection of complement of. So this really should be A intersected with E, intersected with C's complement and B's complement and D's complement. You don't need to mention those, I guess, and that's the convention they've taken in this labeling. So down in the center, we've got A, B, C, D, E. That's the intersection of all 5 sets. Well, what's missing, for instance, do you see any intersection that's labeled AD? A and D are sort of 2 apart, and they don't have a simple intersection. To intersect A with D, you've also got to be inside of E, or maybe slightly out here in C. Yeah, so they've missed many of the regions, aren't there? It's funny that the very first 5-circle Venn diagram that comes up is just wrong, or at least it's not in general position. And apparently it costs $69, so that's weird. What is right apparently is this picture. That's these sort of light bulb pictures of light bulb shaped sets, and you can get all 5 regions that way. But it's actually an area of mathematical research. People try to figure out how to draw Venn diagrams in general positions with lots of sets, maybe 7, maybe 11, with regions that all are the same shape. So they're just moved around somehow. You don't necessarily have to stick with that restriction. So one thing I like to do is use what are known as rectilinear curves. And there is a homework question in this section about using rectilinear curves. What does rectilinear mean? Well, linear is probably making sense. They're made out of lines. Recti means that they're right, or they're horizontal or vertical, right? So I can draw Jordan curves that make only horizontal or vertical type moves, things like that, right? That's a rectilinear curve, and you can easily make a Venn diagram for 3 sets or 4 sets with rectilinear curves. Here's 2 sets with just rectangles. A 3rd set might go on like that. Now, if it's a little bit of a challenge, but I think I can force a 4th set to go on here by just sort of coming in, making sure that I break every region up, but don't break up any region twice. I think I did it. I'm not sure if I did it or not. Now I would have to sit and count all the regions, and I don't want to bore you with that. So let's just guess that I did. Did I pass through all of the regions that were trapped between the green rectangles with that orange curve? I don't see anyone that I missed, so then it should be good. By sort of cutting each of those regions into 2 parts, I get one that's inside the orange curve and one that's outside. So I cover all my bases in terms of creating Venn diagram, all the regions in a Venn diagram. Okay, well that brings us to the end of this talk. Thanks for sticking it out. The next section will be 4.5 in lecture 24. Please read a little bit in advance. Read it all in advance. That's an interesting chapter. We'll see you soon. Have a great rest of your day.